right, that's a good beginning of a song to start at the beginning of a good section here in Chapter 7. The last section that we'll cover in Chapter 7, which is on the dot product. Now, we can add vectors, we can subtract vectors, we can even do scalar multiplication, but we haven't looked at any kind of product of vectors until now. The dot product, which I'm going to define in a second, is used to determine if vectors are perpendicular. It's also used in applications, including decomposition of a vector into components parallel and orthogonal or perpendicular. Orthogonal is kind of the same thing as perpendicular to another vector, and it's also used can be used to find the amount of work done by a force in moving an object a specific distance. So the dot product is defined as follows. If vector v is a sub 1 b sub 1 and vector w is a sub 2 b sub 2, the dot product of vector v sub 1 and, vector v and vector w, notice the big dot in the middle there, that dot in between vectors is the dot product. It's not a regular multiplication, you know, the symbol's the same. And it's equal to the product of the horizontal components added to the product of the vertical components, or a sub 1, a sub 2 plus b sub 1, b sub 2. So we'll try a couple, 3 examples here. It says vector v is negative 2, 6, and vector w is negative 3, negative 1. We are to find the dot product here, which would be negative 2, 6, dot negative 3, negative 1. And so we are going to multiply the negative 2 and the negative 3, and then add to that the product of the 6 and the negative 1. Now I went ahead and wrote it all out like that because I wanted to emphasize that in this case where the numbers go, this is going to be a positive 6, this is going to be, looks like a negative 6, so I get a dot product of 0, which we'll talk a little bit later on. Now what happens if we switch the order around in part B, if we take the dot product of w dot v here, so that's negative 3, negative 1. Got to make sure I'm using the right one here. Dot negative 2, 6. This is going to be equal to negative 3 times negative 2 plus negative 1 times 6. Well, that looks like that's going to be 6 plus negative 6. I get 0 again. And it looks like, with only one example to kind of base it on, so really loose inductive logic, that the dot product of two vectors might be commutative, or abelian is another way to state that. Now let's take the dot product of a vector and itself. Let's see, so that would be negative 2, 6 dot negative 2, 6. And if I go ahead and do the dot product here, I get negative 2 times negative 2 plus 6 times 6, so that's going to be 4 plus 36, and I get 40. Now, this is not a dot product, but I want you to see how it's related to the answer that I just got in part C here. If I asked you to find the magnitude of vector v here, we know that that's the square root of the a squared plus b squared, which would be negative 2 squared plus 6 squared. Now, doesn't that look familiar? Negative 2 squared and 6 squared, and we're adding them. So I end up getting the square root of 40 here, which simplifies to 2 square roots of 10. But notice how this number and the radicand turn out to be the same number. And as it turns out, that's not a coincidence. That's going to happen. And that's a couple of the properties here that I've got listed in the middle of the board that involve dot product. The vector v, or excuse me, u, v, and w are vectors, and c is a scalar, a constant. Then, here was the first thing I talked about, how the dot product was commutative. Now this is a little different in that it says if I take a constant, scalar multiple here, a constant times vector v, and all that is going to be the dot product with vector w, that I could just take the dot product of vector v and w and then multiply by the scalar. So it's kind of a weird looking associative property, but it's not an associative property in its true sense. Now over here, this is going to quite possibly remind you of the distributive property. I have a vector v that has the dot product of a sum of two vectors, w and u. So this is equal to vector v with the dot product of w plus vector v with the dot product of u. Now remember, the dot product is going to give you a number. It's not going to give you a vector. it's going to give you a number. And that number, believe it or not, is going to come into play on all sorts of different applications. Down here, this is the second one I was kind of talking about with parts C and D down here, and that if you take the dot product of a vector with itself, that you get the magnitude of that vector, in this case squared, because I would have to square that to get it equal to 40. So it would be equal to the square of the magnitude. Also here, that if I take the 0 vector, that's not the constant 0, that's the 0 vector, and I take the dot product with any other vector, I just get 0. Not the 0 vector, because remember the dot product is a number, I get 0. And last but not least here, which kind of looks again like kind of a weird associative, if I have this scalar times the dot product, that I can take the scalar times either component of the dot product here, either the vector v or the vector w, and take the dot product that way, instead of taking the dot product and then times the scalar, get the same answer. Don't use this a ton. Definitely going to use this, definitely going to use this, and occasionally this comes into play. Now, there's kind of a cool theme that you can use with the vectors to find an angle between lines, and that is, it says, with the dot product, it says, if I have two vectors, v and w, and I try to draw them out over here, this is vector v, this is vector w, in standard position, notice the initial point is at the origin, and the angle theta between vector v and w, which I've drawn right in here, is formed by the two line segments representing those two vectors, because that's what those are, line segments. Those are not rays. Remember that the arrow just indicates direction, it doesn't mean it goes on forever. And we're going to keep theta here between 0 and 180 inclusive. Then the angle between the vectors, if theta is the angle between the two non-zero vectors v and w, then the cosine of theta is equal to the dot product of vector v and w all over the product of their magnitudes. Now, these are both dots, but this is the dot product, and this is just regular multiplication, because remember, the magnitude of a vector is its size, is a number, is a constant. Same thing over here. So I'll be multiplying two numbers, but up here I'm taking the dot product of two vectors. So let's try an example of that. Find the angle between vector 5, negative 1 and vector, I didn't give it a name, let's call it v. V is 5, negative 1, and vector w is negative 5, 12, and we'll round our answer to the nearest tenth of a degree. So, if I want to find the angle, I'm going to say that the cosine of this angle is equal to the dot product of 5, negative 1 dot negative 5, 12, and then that's all over the absolute value, the magnitude of vector. What is like an absolute value? The magnitude of the first vector times the magnitude of the second vector here, negative 5, 12. Careful with your arithmetic here, lots of places to make silly mistakes. So this is going to be 5 times negative 5 plus negative 1 times 12. Down here, this is going to be the square root of 5 squared plus negative 1 squared times, this is going to be the square root of negative 5 squared plus 12 squared. So up top, here, I'll bring it over here, this is equal to negative 25 minus 12. On the bottom here, that's the square root of 26, and that turns out to be 13, the square root of 169, 13. So that gives me negative 37 all over 13 times the square root of 26. Now, we know that cosine is negative in the second quadrant, so we're looking at a second quadrant angle here for these two vectors. And what would that be? Well, the cosine of theta is equal to this. Now, this is again, and I brought my calculator here. So this is a good time to get the calculator out and to grind all this stuff out. So I'm going to take negative 37. By the way, you can rationalize that denominator, but that's not my final answer, so I'm not really so worried about rationalizing it. So I have negative 37 divided by 13 times the square root of 26. And I get this to be negative 0.558 817,669, and so on. So now I'm going to take the inverse cosine of that. Hopefully I have kept my calculator in degrees. We'll find out in a second here. Negative 0.55817,669. And I get 123.929, and I think it said rounded to the nearest tenth of a degree, so we'll leave it at this. So the angle between vector V and W, vectors W, there we go, is 123.9 degrees. And that again is to the nearest tenth. So that's kind of a neat little problem there where we could find the angle. If you wanted to draw this out so that you could get an idea of what it looks like in standard position, I think you'll find that the angle formed would be obtuse and that this would make sense and hopefully would look very similar to what you have drawn out. Now we have lots more to do using dot products, so we're going to go on